Okay, now we're going to hear from Zhisheng Shuai, the University of Central Florida, about Lyapunov functions and global convergence.
Well, thank you. Thanks, Olivia, and all organizers for this opportunity. Really, the primary hat I'm wearing for this workshop is a newcomer and a learner for this topic. So, and after recognizing there will be a talk tomorrow on global stability, I would like to restrain myself for the models for non-evolution dynamics. So I will show you the lessons we learned by working on these population models in ecology and epidemiology, and particularly on this Lyapunov function. Okay, so if I may, let's see. Okay, so this is a really simple toy model. It's a logistical model. We can show that this equilibrium, it is globally asymptotically stable. Here the stable, there's so many words of stability in evolution dynamics. Here means Lyapunov stable. And the global stability here means it is global convergence. So it means if you have initial conditions for this model, as long as your initial condition is positive, then all solutions will approach this positive equilibrium, which is the carrying capacity. So there's a different way to prove the global stability of this positive equilibrium. Here, I list two Lyapunov functions. I want to show you Lyapunov function can be not unique. Okay, so, and particularly you can see this function is non-negative, and the derivative of the function along the solutions of the model will be less than or equal to 0. And then you can show this is a Lyapunov function, and then all solutions with the positive initial conditions will approach this positive equilibrium. So this is probably the scalar equation, probably the simplest one you can think about. But since we are getting more complicated, so let me show you the general theory behind that. It comes from this this Russian mathematician Lyapunov. So if you have a system of different equations, let's stay with ODE, and X star is the equilibrium. Basically, that make the right-hand side of the different equation will be equal to 0. And then if you have this function V, such that this is satisfy this non-negative and vanish at this equilibrium. And also, as we said just before, the derivative along the solutions of the system will be less than or equal to 0. Really, you are thinking about along the solutions of different equations, your V value will be non-increasing, okay? So then we call this a Lyapunov function, okay? So to show the stability, they have this Lyapunov stability results. And if you pose a little bit more kind of restrictions, and you can show this is asymptotically stable, means convergence. But we are interested on global convergence or global stability here. Really, you want show this Lyapunov function would work in this the whole basin of attraction of this equilibrium. So I think the challenge comes from the whole basin of attraction. So of course, the background is come from the energy function. And really, if you think about the physical systems, you can have defined energy function. For example, let me show you the example. This second order kind of damped oscillator. X is the position, X prime is velocity. And if you have a damping coefficient, alpha is a non-negative, and Fx is a distorting force, you can show the trivial equilibrium, means your oscillator will stop oscillation at position 0, which is globally asymptotically stable as long as your positive damping coefficient alpha. Okay, so you can use this total energy, this kinetic and potential, and add the Lyapunov function. And of course, here, if you look at V dot equals 0, there's some kind of issues. You can show V dot equals 0 will align along a line, which as long as Y equals 0, you have infinite many points here. So in order to show the global convergence, you need to use this Lassalle invariant principle. Use this kind of omega limit set have certain property there. But nevertheless, you can find this energy function as a Lyapunov function. Okay, so now if you think about you have this biological systems, you ask what kind of energy function or what kind of Lyapunov function you could have. So I guess I kind of skip one important part. If we go back to this Lyapunov function, of course it's quadratic, but this is the first integral of this logical Wataka system. So that's why people, particularly, I was reading a book by Hofbauer and Sigmund, which I probably bought like 2 decades ago, but I most recently read it. I found out there's a lot of new things, and which I didn't understand back at the time. Probably I still don't understand now. but really, there's a lot of questions. I showed my interest, and there's some nice comments. Definitely, I will look into that. Okay, so also I learned for. I said I should stay away from evolution dynamics, but I learned that a new type of Lyapunov function had been used in this evolution dynamics, which I didn't know that. Okay, so that's really a new thing for me to learn. So really, I would like to look forward to the talk in the workshop and also particularly the talk tomorrow. Okay, so let me go back this one. Okay. So probably really Lyapunov function not only has been used in dynamic systems or in mass biology, but go beyond in control theory, engineering. They use the Lyapunov function for other things. Okay, at least a bunch of things. And but the challenge comes from nobody tell you how to construct the Lyapunov function. They even have this inverse theorem of kind of Lyapunov stability. They say if your equilibrium is stable, that guarantees the existence of the Lyapunov function. But still, nobody tell you how to construct it. So that's bring this page of this challenge. So of course, our challenge is to establish the global stability. So as I said, based on attraction. So it is a very challenge, okay? And particularly when you have bistability happens. So I didn't see any good Lyapunov function works for bistability, give you this largest based on attraction yet. Okay, so but however, the model I will show you, they don't have bistability. So that's why we should be able to construct some Lyapunov function. And I think the good example would be the model from this epidemic model. So this is a classical SEIR model, susceptible, exposed, infected, and recovered. So if you look at the equation, it's 4 dimension. But if you know that R does not appear in the first equation, that's 3 dimension. Okay, I show the first example is a scalar. Second example, couple of oscillator, 2 dimension. So 1, 2, 3. Shouldn't be that hard, but I can tell you the positive equilibrium of this model has been open since 1970 to 1995. 20 plus year open problem at the time. Nobody can solve it because 3 dimension. Poincare-Bennigsen theorem does not apply. Okay, there's no Poincare data. So what we learn in the ODE2 class does not apply here. People cannot rule out the existence of periodic solutions in the 3-dimension space until this. Let me skip the page. Okay, I assume this audience are familiar with this kind of model. But if you're interested on that, I can show you the slides. So, but what for disease model typically is you have disease-free equilibrium when R not less than 1. Okay. And less than or equal to 1, that's easily globally stable. When R not bigger than 1, the disease-free equilibrium located on the boundary become unstable. And you have fixed point or kind of positive equilibrium called endemic equilibrium. People suspect this positive endemic equilibrium will be globally stable as long as it exists. Means R not bigger than 1. Okay. So when you prove the global stability of the boundary equilibrium, because the flow, the dynamic system has kind of monotone property, you can use kind of comparison argument. And I want to show you they do have the Lyapunov function. If I want to draw attention, the first 3 terms here, it is the same as what are Lyapunov function I show you in the single species model. And this type of Lyapunov function has been so widely used in ecology literature, probably many years. Okay, but not that much in disease model until probably after 2004. I mean, to solve this complete kind of global stability problems. Okay, so I think this is a nice phrase: biology inspiring mathematics and mathematics inspiring biology. But I want to show you this slide. Really, the biology problems inspiring the theory development of mathematics. So, because to prove the global stability of endemic equilibrium, Michael Lee and Jim Downey back at the time, they extend this Pangler-Bennington theorem from 2 dimension to higher dimension. They use these compound differential equations. Their proof is about like 10-page long. Okay, so people might not like it. Okay, but however, this is a very effective approach to show the global stability for 3-dimensional system and higher. Okay, so I believe Kolobennikov, when he was doing postdoc with Philip Manny knew the result by Lee Downey. Probably I suspect he didn't like it, and probably he challenged Kolobennikov whether he can find the upper function for these disease models to prove the endemic equilibrium it is globally stable. It turns out he did. That's their paper. Well, I want your attention. They have 3 terms. Each term is a Wurtler type Lyapunov function. What his main contribution? I should say both of them, because Kolobennikov published some other more papers. Okay, so what their contribution is, find the right coefficient in terms of each building block. And if you remember, I take a derivative along the solution of the differential equations. If I take a derivative, I have so many terms there. They find a nice way to tell you how to group those terms come from derivative. And for each group, they can show that less than or equal to 0. So 2 challenge, find the coefficient and how to group those terms after you take a derivative. Okay. And then since 2004, many people following their kind of technique and use the upper function to show global stability of many epidemic models. So that's really is the upper function has been widely used in ecological models many years, and probably 20 or 30 years later had been used in disease model. So we are thinking evolution games or evolution dynamics. So we will see. And let me tell you what we did. Oh, another thing is very interesting. If you pay attention to L and V, one is the upper function at the disease-free equilibrium, I equals 0. The other is endemic, I is bigger than 0. Those 2 equilibrium collide when R not equal to 1. That's transcript bifurcation. Okay. So what you can see here is, if you let positive equilibrium approach disease-free equilibrium, you let E star, I star opposite 0, S star opposite S0. It turns out the limit of V is L. So essentially, they are the same Lyapunov function. Maybe this is the energy function for digital model, or go beyond. Okay, and I can tell you normally it's easier to find the kind of Lyapunov function for boundary equilibrium, but it's very hard to find positive equilibrium. Can we do? If you recognize if this is still true for more complicated model, can you go reverse process? Would the existence of the upper function for disease-free equilibrium help you to find the upper function for positive equilibrium? So we are working on that, and we check many models. We stuck for something, but I think we are making some progress. Maybe that can be continued in some other time. Okay, but let me tell you the things we have been thinking. Let me skip those 2 pages because that's more disease. So as Hephesco in his SIM review paper 2000 point out, this model, MSEIR model. Now, remember I show you SEIR model, okay, later on. Now, in his SIM review paper, Hephesco include another compartment. It's M, means that the newborn baby has a temporal immunity. After a few months, the newborn baby becomes susceptible. Increased by 1 compartment. I can tell you, this model, the positive equilibrium, endemic equilibrium, the stability, global stability is still open. So as he pointed out, that's 2000. Okay, we try work on that after we learned from Kolobennikov. Many years failed. Okay, so I'm sorry. So, but still open. So if somebody has good idea, that would be a nice thing to try. Okay, so. However, we are able to do something to answer another question asked by Hephesco in one of the notes from summer school, 2002. And he asked, there's a paper back to 1976, Lyapunov and Jim York work on this N-group SIS model. You can think about this, SIS is for this STI, sexually transmitted infections. Okay, they have different behavior group, okay, core group or different group. Or you can think about you have different age group for childhood disease. Maybe not for SIR, should be SIR model if it's about measles. Okay, so in their 1976 paper, they were able to show this endemic equilibrium, it is globally stable as long as R bigger than 1. Okay, and have Hertzko ask, how about N group SIR model? I think they say this is open. So we were working on that problem. And what we learned is what we do is we use one group model, the Lyapunov function, as a building block, and to build this N group model in the following way. Just weighted average, just add them together. Okay. So the physical kind of analog is simple. You have an energy function for small system. You want to get an energy function for a couple system. Just couple this energy function together. But the coupling coefficient, we have to use this kind of graph approach way, graph theoretical approach way to do it. So what you can do is you take a derivative from this CIVI, because normally your model is really complicated. You have this coupling term. As you take a derivative, the coupling term appear in this form. So think about your coupling have I group to J group. Okay, you use this coefficient to build a graph, and use this graph you can find the cycles on graph, and then you're going to check along the cycles of the graph. This f functions atom is less or equal to 0. So really, this theory, this approach tells you how to depict this coefficient, okay, and how to group those terms after you take a derivative. You're going to group those terms along the cycle. So that's use this approach. Because of time, I will not show you the details. And the things come from this Laplacian matrix and the cofactor, or the eigenvector of Laplacian matrix. You use the graph theory, so-called matrix tree theory. Let me skip the page. So let me skip the page. Okay. So the results come from here. It's a new group that's a double sum as kind of cycle in the graph. Okay. So maybe take home message would be use this kind of approach, building block. We are able to use one group of small system Lyapunov function to build up large system Lyapunov function, and this approach go beyond this multi-group kind of disease model with many applications in disease models and others. So I think really by reading the book again, there's a lot of kind of questions which I'm writing a list. So, but certainly there's more questions. Maybe some of you might have. I would be very happy to look into that. And nevertheless, even with a disease model or ecology model, there's still some open problems which we do not know. Hopefully, we can motivate some kind of new theory in the future. Let's stop here. Thank you very much.
Thank you, Zhisheng. Awesome talk. I have a question really quickly. Am I allowed one question?
Yeah.
You may know it dates back to Bartlett that the stochastic version of this SIR or even SCIR model, which would otherwise have an internal equilibrium, has persistent oscillations. So basically, stochastic resonance conditioned on non-extinction. Yeah. So two parts of the question, like what does it matter that there is a global asymptotically stable internal equilibrium that's fixed if the sort of discrete, the more realistic discrete model like will have sustained oscillations? And related to that, what does the Lyapunov function you've constructed mean even for the stochastic model?
Even depends on what kind of stochastic model you have. So what kind of noise you incorporate?
Demographic noise, yeah.
Right. So if demographic noise, you could have this. People use the Lyapunov function to show the existence of this invariant kind of measure, which is kind of stable. So in other words, if you look at the density function, that will be along this equilibrium, or you have oscillations, you have these things. I think people have been using the Lyapunov function to do it. So I think you basically you're going to take use the Ito formula. You're going to have some extra terms here. So you need to put assumptions on those kind of extra term. So basically your drift term will dominate. Let me say which term. So noise term will be dominated by the drift. So basically, yeah. So thanks.